All right, that is going now, finally. Let's see, we're partway through this. I think we're somewhere here on the anger cameras. So I think we had just ended up on this. I'm going to start here just because it's got the overview picture, though. We'll finish this up and then we'll talk about a simple intro to expectation and expectation analysis. So remember, we've got our patient who is both the thing we're reconstructing and our radiation source because we inject the radioisotopes in. The collimators basically will take care of depth problems. We mentioned there's different types we can do depending on what we're trying to aim towards. You know, are you trying to get better resolution to a smaller area? This is often used for hearts, so we talk about cardiac perfusion. So aiming at a smaller organ makes a lot of sense. Do you have to do a really broad body area, in which case you're just trying to say where in the body in general might there be cancer bits? You know, you go here. So there's several different sizes you can go in between. Scintillation crystals, we'll talk a little bit about that today because this is one of those areas. I don't know, does anybody have an interest in materials? You'll find out why some materials matter to us. So materials is an ever increasingly important area of almost every branch of engineering. So even if it's not your main thrust, understanding what those materials trade-offs and what you have to do with them becomes kind of important. Photomultiplier tubes, I believe we talked about that last time. We have our position logic circuit that goes on for determining what got hit and sending the positions out. The pulse height, which is going to help us to determine, do we want this? And then we'll have a gating circuit that says, should the computer input that point or not, based on all the inputs. But we'll talk a little bit more about the positions off them. The only thing I did is I noticed I didn't really have a picture of a scintillator before, and I actually grabbed a couple scintillator materials. And I don't know if the book mentions this one, but this is like the standard. If you're doing anger cameras, you know, you are doing sodium iodine as your scintillator to it. It's got some certain things we really like about it. You know, it's doped with thallium, so atomic number is 81, so it will absorb an awful lot of stuff. It's got a ridiculously high light output. Almost every other scintillator out there expresses its light output, usually for ratings, as what percent of what sodium iodine would output. You know, and you'll get people say, we get up to 70%, right? So it just kind of gives you an idea just how crazy high output this is. The disadvantages come right here, right? In addition to these other nice properties, it's cheap as hell. Right, so it's a long time use one. It's a fairly easy one to produce, cheap relatively speaking in this category, but it's still, you know, it's barely affordable. Decay rate is slow. It's about 230 nanoseconds before things drop down to 1/E. So that's a pretty slow area. For when you're dealing with anger cameras, that is not a disadvantage at all, though. For the anger cameras, you just want to know what the overall intensity is. So that slower time, in essence, is going to do a time average because they're going to build up on each other, and who cares? That's binning, right? So it's kind of lends towards binning. Now, it will have an effect. You know, very often people will do things to try to shield one area from another. That's another purpose of separating the crystals out so that the light doesn't spread too far out to other areas because it lasts so long. The other thing is it's not very dense. Right? Most of the more expensive, you know, fancier ones that have really good decay rates and things like that that come in later are about twice this density. So these two deficiencies right here will make it completely unacceptable for PET. So the first couple ones they tried to do in PET, they tried to use this because it was like the standard. didn't work. So we'll talk a little bit about what those other materials are when we get to PET. So I thought it was worth adding this one in because otherwise it doesn't do my PET discussion very well. Mix-ins, what we have on here, I think we talked about. There's not much to the configuration that's on here. If you've got cylinders, what are you doing? Oh, this is probably worth noticing. Remember I was saying the light and everything else? You will almost never see a practical one of these that you buy that doesn't have metal wrapped on the outside of it. And a big chunk of that is actually, well, it's twofold. One is to prevent the light carrying out because it's completely opaque. The other one is you have electrons that are generated by these, and so you can ground those in between and prevent electrons going out from the other ones and causing nearby scintillators to act on. Anyway, if you're dealing with the cylinders, which are pretty common to be able to generate, because a lot of these you kind of get a bath of them, and you have your start seed and you pull them out, so you get these cylindrical shaped crystals. It's a pretty natural one. You smooth grind out the outside, and there's your scintillator. Therefore, it leads to this, what's called hexagonal closest pack. It's the densest way you could pack soda cans or whatever else in, right? So you go to materials and they'll do this, and they'll do tennis ball packing and things like that, the 3D equivalent. If you've ever tried to stack glasses on a shelf, you'll discover if you put them online, you get this huge diamond in there, so it's a bad waste of space, right? So this is about as dense as you can go, and you can see it nicely lends itself to making these kind of hexagon shapes as they build out. So anyway, if you ever like playing games and you ever see games often go on hexagonal grids, this is the same reason. Because what it means is when you're fighting opponents or whatever else, this one means that it's putting your opponents all at about the same distance, right? Because otherwise you've got that long reach to a diagonal. So again, it's got that same exact implication, whether you're packing cans, whether you're figuring out molecular crystalline structures, or whether you're trying to figure out how to shoot your friend in the game, right? It turns out to all be the same dumb thing. That's kind of one of those nice carryovers that makes engineering possible in the world. All right. So I mentioned this the previous time, but we didn't go into it. So you can see if you take a look, we want to be able to figure out the pulses in here and separate which ones are the ones we want. We don't want photons that have Compton scattering going on, because if there's Compton scattering going on, it's deflected, and so we don't really know where it came from. The neat thing is as you are getting basically the Compton, remember Compton, you lose some energy when you get that angle that's going on? Well, since I lose energy, the energy drop actually allows me to be able to detect Compton scattered versus non. This does not work in normal X-rays. Why?
Because our source is monoenergetic.
Yeah, it's not a monoenergetic source, right? You need a monoenergetic source to be able to do this, but we have them. Nuclear reactions are guaranteed to be monoenergetic. It's as monoenergetic as you're ever going to get. So therefore, when it actually comes to us, right, we have, this is the tiny amount, you'll get a little bit of degradation by stuff that's in there without any significant scattering. Compton scattering takes enough out of it that there's really kind of a good dead zone separator between those that have been Compton scattered and those that aren't. So the nice thing is we can look at that and just in advance on our detector, take a look at scanning, pick out what the acceptance windows are. Right? And so away you go on those. Yeah. And how wide you pick this actually becomes a little bit of a design parameter for something going on. The wider you pick it, the less precise you're getting, but the more hits you're getting. So if you're having to do something where it's going to be really narrow and the amount of radiation is coming out is smaller, things of that sort, then you might have to accept more just to get larger number of counts, for instance. All right. This makes sense. I mean, this is one of the easier ones. It's basically just setting up a threshold. The number of pulses, and that is obviously, you can tell when you're looking through them which ones are here, and it's based off of the energy.
Oh, actually,
Yeah.
I do have a quick question. So in proton CT,
Yes.
sometimes protons hit a nucleus and shoot out another proton that's faster than the one that came in.
Yeah, they can. Yeah.
Is there anything like that that can happen here? So you have to upper threshold your pulse height?
No.
Okay.
That's because really photons don't generate any type of nuclear decay. What you'd have to have is there's a very, very rare chance that a photon is going to get absorbed by a nucleus.
Okay.
And then that nucleus is going to emit.
Okay.
Right? But if the nucleus absorbed it, then it will emit at exactly that energy.
Right.
So there'll be no gain from it.
I see.
That's going on. The only thing you get is you get a displacement error, but given the change in direction, it's not. And it is such a rare thing. You might only get one or two in the whole. You're not talking a large number. So it won't cause you any significant difference. So let's kind of talk on these ones. So there's several different modes. I included this partially because of my interest for PCT, because we also have similar types of modes that go on. The most common one that we deal with on PC is this one called list mode. Every time an event comes in, right, a proton, in this case, you've got a particular photon that's coming in, and you just get a list of all the events timestamped. And really what's happening is those timestamps are generally increasing. There can be some slight alterations in if they're really close times and one of them is closer to the control board. Sometimes their particular one will reach the control board before the other. So I wouldn't say it's strictly increasing, but in T, but it's pretty darn close to strictly increasing in T. So that's one common way. You just get each of these individual photon pulses, and away we go. The rest of these ones are kind of some more specialized things. So in a static frame mode, what we'll get is, basically you have a preset time slot and you get all the ones that kind of hit in that zone. So they're trying to show it by showing all the different ones and you'll get your counts and all that off of them. There is a dynamic frame mode that goes on. So the static one, that time frame is basically your whole thing and you get the bid across them. In a time frame, I've got little slices and I find out in this particular time frame, how many hits did I have in that whole thing? So I guess in some sense, they probably should just stack those, but cheaper to do this. There is a special variant when you get, particularly, right, so the multi-gated acquisitions is what they're calling, and that's the fancy term. But this is really used for what's sometimes called 4D CT type things. So imagine you're trying to take a picture of the heart and you're trying to reconstruct it, right? How do I actually do that? Because your heart isn't constant. The shape literally changes, right? As it contracts, the heart is a different shape. So how do you reconstruct that?
You can pick a time or make a periodic model.
Yeah, so imagine this. Imagine I took and got a model of your heart. So I could do this by taking a CT one, which I can do really quickly, and I can break it up into these areas. And I can get a breathing model and a heart by hooking you up to an ECG. I can get where in the pulse train that your heart is, right? And I can, with your breathing, right, because as your lungs move, it's going to move the heart's position. So I can just hook over your mouth a mask, and I can take air coming in or out. And so I can take this, I can do CTs, and I can just slice this up into little periods. And there'll be periods when you're hitting the maximum air and your heart is hitting that R pulse they mark up there, right? And I can correlate all these different possible combos, right? How much air is coming in or out against what phase of the heart I'm on. I get a little 2D matrix. And at any time I acquire one of my measurements, I can stick it into whichever one of those boxes it goes with, right? So I can say, you know, I'm breathing in at this particular point, and, you know, I just had Q happen inside of my heart pulse, right? And as I look at each one of these and I say how it correlates to the phases, I can just reconstruct it by kind of binning batching it in. This is done in 4D CT. We do it over here. We do it in a 4D version of, you know, any imaging actually. If you want to image something, one of the easiest ways to do it is to kind of get these bin categories. And then we reconstruct a different image for each of those bins. All right? Once we've done that, right, so I can just do that, for instance, for regular CT. Then I've got a full model of where your organs are located at any given time period. I've just got static frames of this is your R pulse at this stage in your breathing. This is your R pulse at a different stage in your breathing. All right, so I've got all these things, and I can now animate your body. I can also calculate deformations where each of those ones move between any two states. All right? And so all I have to do now is just make a differential equation. Usually it's a partial differential because the volumes are changing as it's going in, so it's much more like a fluid flow. But we basically do a map between them. And then now I know, based on whichever of those states you're at, I can recreate the spatial area to go to a single static module. Yeah.
So you're saying frames, so you create like almost like a video
Yes.
of the heart beating, the X-ray data.
Exactly. All like
And then when this happens, like what is the resolution usually on the, or like what's the time frame resolution? Like,
okay, so figure your typical pulse rate if you're a person resting is say 60 to 80 pulses a minute. For simplicity's sake, somebody resting, maybe we give them mild amounts of sedative, and then easy calculation, you get about 1 heartbeat a second. There, you know, I mean, it's often like 0.8 for some, but by the time you're laying down, it's probably pretty darn close to 0.9 to 1, somewhere in that zone. So I'm just going to call it 1. All right, so essentially, you go through all these stages. The largest period, it's not quite as much as they stick it out there, but it's a big chunk of it is this rest zone in between. So this is an alternative way of doing it, right? Some people just take out where the big part of the pulse is and they find the quiet period of the rest of the heart before the next beat comes in, and they just do everything that. Because then you really just have one frame. Right? If you want what I'm suggesting, which lets you use everything, you kind of divide up this stage, and you can see that I've got periods, right? I've got the R and afterwards, right? I can take each of those periods, and exactly as you say, it's kind of like a little flip book. And I can calculate, you know, basically by just putting the measurements. When I take the measurements, I find out I'm taking an ECG, so I stamp it with what stage of the ECG that measurement came in with. And I also stamp it with the tidal volume of your air. How much air has come in or out, so I know the inflation volume of your lungs. Those two ones together let me put you to the bin, and I can do the animation of your heart and lungs now. When I do that, I can now map between them using a partial differential equation of a flow, and I could say what one tiny volume inside of the heart for one thing, what a voxel on that, what would it deform to in one of the other states? So therefore I can map all of them to one state. Usually the resting position, because that's your the most number of data. So you might as well move the smaller data to the non-moving one, plus you get less motion artifacts from it. So I just map everything back to the resting state, and now I take all of your data to there. And now what I'm doing is recreating a resting version of your heart. Right, so I can make a single picture out of it by taking the CT's morphology, which remember, it's going to have really good geometric qualities. So I know it's accurately where things are, so when I'm just trying to move things, I can move them accurately, i.e. change the XY position. Does that make sense?
Yeah.
So that's basically the area. But yes, if you collect enough data, you can also get the animated version. And you might even want that, particularly when you're trying to do some of those functional things. When do you get the best blood flow around your heart? At what stage of the pulse? Right? You might care about that rather than just, does the area get blood? If I'm just checking for your overall health right now, I care that it's getting blood flow. But when it gets its blood flow could indicate things like how plugged up the particular blood vessel is, things of that sort. How is the flow moving? So therefore, it might be helpful to actually split those out. I don't know of anybody right now for SPECT who's doing a true 4D type image to these. They always, all the ones I know of, map it back to a static image. And, but I would say this, I think in the future of pretty much every medical imaging, and the future, I mean next 10, 20 years, I can't imagine anybody not including motion into it.
Yeah.
There's too many potential pieces of information that you would lose. And there's an awful lot of these ones that actually allow you to acquire CT scans simultaneously with, other scans, or even MRIs and PETs at the same time, things of this sort. So multimodality ones, which is what I need to do this type of a remapping, are fairly standard now. You can buy off-the-shelf equipment that does it. Anyway. The photon ones are particularly nice with MRI things too, because the magnetic field is not going to deflect your photon, right? It's not a charged particle. So. All right, all very good questions. So you can see the other one here, like I mentioned, just the frame. So just remember the second option is to just during the area, the dynamic parts of the heart as opposed to the resting phase, you can just turn off acquisition. All right. And if you slow down people's breathing, right, you get them to relax. Sometimes they do this with anesthesia. You generally don't like to do anesthesia if you can avoid it, because anesthesia might actually change some of the things you're trying to measure. So ideally, you're trying to measure something in your normal operating. If when I give you anesthesia, that doesn't appear, it might invalidate my test. So ideally, we would like to avoid it. There are, however, some people who get so nervous with these machines because it's a machine around you and it's moving, and I'm in a room by myself, and a lot of them have tubes and you're partially in a tube, and the closer the machine is to you, the better the image. So it's a small space. You'll get people who will seriously freak out on these things, in which case you might not have. And it's true. Children, you can often give them a teddy bear or something like that, and so they'll have ones that are made of materials that won't absorb a lot of stuff, so they're basically invisible, so you can hug a little bunny or whatever. Kids will often come down, it's usually freaked out adults who are kind of worse, to be honest with you, because they're bigger, and if you hand them a little rabbit to hold or something, they're really not going to be happy with you. And you kind of, by the time you become older, any fears you have are more set in your pattern of reactions to them. So in some sense, they become a little bit more difficult to control. Whereas with a kid, it's kind of new, and you have a lot of things naturally that your parents are teaching you to sleep, particularly when they're small, you know. So they'll do something like give them some food, give a kid warm milk and something like that, and you know, a little stuffed animal, and they're pleasantly snoozing. So anyway, interesting. There's actually a lot more you can do with kids, but that's another whole thing. Anyway, I just thought this was interesting. Different ways we can slice it up allow us to handle different things. And this one in particular lets us go into 4D things. And that's really what they're trying to show with this cycling around is we're going to rebatch them. Think of this as, you know, our phase of the heart with, you know, breathing at maximum, so on and so forth. And so you just, as the data comes in, you shuffle it into its appropriate bin. I can then take these also and stack them to walk down your whole body. These sensors are nowhere near big enough for your whole body, so you know we might have to do your head and then your chest and then your abdomen, so on and so forth. And that's what they're trying to show with this, is you can just stack them. All right, collimator. So when we look at the collimators that's in here, I had mentioned that it gives you depth. That's really what the little picture in the upper thing is doing. You see there's a particular you know, width of the opening and a width of the thing. So they call them D and H, right? The scintillator is B, and how deep it is into the collimator is that little L. So you basically end up with a triangle that is D by L. You can kind of see the dotted lines coming out or the solid lines. The rate of those is going to be, you know, your L is your height increase, so L over D. Right, that's basically the slope. And then you'll just have the plus or minus version of it, whether it's going up or down. So you get those, and then that separation width actually also helps you to kind of remove some of them. They get absorbed if they hit weird. You know, and then the scintillator crystal, you really want these. So there's a competing situation here. You want them really thick to guarantee you get the high energy photon captured. Right? The thicker it is, more likely photon get captured, generates light, goes out. The problem is the thicker it is, the more likely that photon gets absorbed inside that high Z material, and the photon doesn't get out. So now you've got a trade-off. I want it really thin to be able to detect it, and I want it really thick to be able to capture it. So now you're stuck with a trade-off. Usually you end up with something, you know, often, you know, 1 to 3, you know, centimeters. Not a huge thickness to them. Yeah. Anyway, it's fairly thin scintillation material. You get quite a few that are less, you know, down on the millimeter scale too, that you'll see. And it'll depend. One of the properties of the material when people go through and pick them is how well does this material emit light? How well does it capture things? That's usually a function of density and Z. And then how likely is it to recapture? You know, so this is, you know, usually called LLOS, light loss LLSO, light loss to self-absorption. Yeah, and it just, you don't get photons out. So that becomes kind of a crucial feature to us. These letters on the side here are just, remember we had the different shapes? That's actually all these are, right? Ultra high resolution, you get the smaller ones kind of aimed in to you're most directed at something, you know, high resolution, your all purpose is going here, and then the high energy sensitivity is just going to set it so that you have the bigger D in that one, which means you're going to allow more to come in, but you kind of lose lose the resolution often. So rather than say not great resolution, they just call it high sensitivity. Just mean we're more likely to capture photons because these are just spread farther apart. So, but that's another one. So these are just kind of standard, and they just build all of them, and then you just swap the colorimeter out that you want. Sorry, collimators. Okay. I thought it would be good to give you a picture of a few of these. You know, that one's the book one. I give you this one because this is a 3-1. And I want to give you a 3-1 because there's 2 different types of 3-1s, and the book talks about it as if there's only one type. So there's this, which is really used for the 360-degree whole body scans. All right, so you can see with both of these types, they're designed to rotate around you. Right, that's why it's a donut-shaped area. You have these beds. You can see these center parts here are separated out. They're robotic. So the person lays down at their comfort level. You can adjust the height on this bottom area very precisely. You can see the accordion folds coming up. That's all height adjustment to get in line. And then the bed will slide on a track here. You can see the track area. So that can slide in to get whatever part of the body is necessary inside. That's all remotely controlled from a booth so that you can slide the person in or out. They try to leave these areas open in between because people freaked out when they were closed in. If you see old models, they're closed in, but then it was this long, really thin tube, and the number of people who freaked out was very high. So if you look at old ones, they're completely closed off tubes, but it turns out just these little openings will help a lot of people stay calmer that's on it. And of course, they go around. You know, each of these cameras just gives you extra stuff, right? Those are at 90 degrees. They have some of these where they're 180 degrees apart. I've got 2 choices I can do with these, and the book will has a table, which I'll show in the next thing. But I want you to just think about what I could do with them, right? I could either increase my rate of capture, right? I've got 2 ones at different angles. I therefore don't have to do that angle, right? So I can capture it at a much quicker rate that's on. You can think the same things here, right? I only effectively have to measure 60 degrees worth to get a 480 or 120 to get the full 360, because they're 120 apart. So I can speed things up. Or I could take each one of those through a 360, in which case there I've got twice as much data, and here I've got 3 times as much data. So I could also use it rather than, if the time frame doesn't matter to me because I need 10 minutes and I can rotate this, I can use this for better resolution. So it gives me kind of a trade-off of multiplicity. And this is kind of crucial. This is a 360 scan. There's also 180 scans. Now 180 scan, you know, well, why do you think I have both 360 and 180?
Well, because the photons are going from the middle of your body, you can't see the bottom half of the body just doing 180 degrees.
Why not? Sometimes the bottom half, photon comes out.
I mean,
just think of like just even a straight X-ray position, right?
mm-hmm.
If I'm firing an X-ray through your body, right, I'm going through your body.
Right. But I guess if the photons are coming, if like, just imagine there's a cylinder source inside you. The photons that go the other way are going to pass through the bottom half of your body and they won't hit the detector.
Yeah, but they will here, right?
I guess, yeah.
Because it's going to rotate around.
That's true.
And these beds are usually, they make them out of carbon fiber. And the reason is carbon has a very low Z, but carbon fiber is very stiff. So it won't really appear on your image very much, but it's very, very stiff, will hold people well. So, you know, it's lightweight. So usually those slide-in beds are something like carbon fiber or something like that. That's essentially going to be invisible. The radiation will actually damage them. So like every 6 months to a year, they become a little more brittle when you just throw them out long before it's ever a problem and just replace them. But you'll be able to see all the way around. right? And it's designed, you go right in the middle of that bad boy. Here it looks like it's on top, but this can actually rotate around you. It has to, otherwise you'll only get 2 views. So there are some that will only do 180, do a front side, but it's kind of an odd thought. Now, here's the why. Imagine I'm imaging my heart. Where is my heart? It's a little bit to the left, right? Is it more front or back?
I'm not there.
Where do you do CPR?
Front,
Why?
it's closer.
Yeah, because it's close to the heart. So you do actually have reason to make that type of a guess, right? Because otherwise, if your heart was way to the back and it was easier to pump the heart from the back, people would say flip the person. But your heart is more to the front. It's not completely front, but it's more front than center, right? So therefore, think about it. If you're trying to image the heart, the quality of the photons you're going to get, will it be the same out the front or the back?
Better at the front.
It'll be better out the front. And think of what's in the back. A really giant bone structure, right? That's where your spinal column is. Your ribs are at their thickest in the back because that's the attach, right? So you got a lot of dense structure back there, which absorbs photons more. So not only does it go through more material, but it's more and denser material, right? So from the front, the only thing competing from the sides and everything is your lungs, and that's just air, so that's really not making much of a difference, right? So the quality of image you get from a SPECT system out the front is way better than the one out the back if you're doing a heart scan. So if you're specifically targeting one special organ and you include the stuff from the back, you actually worsen your image. Right? It's one of those cases where more data doesn't always help you. It matters the quality of the data. So this is kind of, there is actually some controversy over this type of thing that some people go, well, if you process that stuff and account for the instability, you can still get it. The patients are getting the radiation. And other people go, nah, but I can get more measurements if I put the detectors all to the front all the time. So there are debates that go about this. But I mean, just plain and simple, physically speaking, I am definitely leaning towards the group that says it makes more sense to take them from the front. Because the corrections I have to do to fix the other thing will never be as good as if you just collected good data in the first place. You know? Anyway, but there are debates that go on about this. So I'll show you some pictures that relate to what do you do with the triple scans when that goes on. So here's the books table that kind of tries to account for that. The relative sensitivities is just talking about, basically it's taking how many planes. If you notice, that's exactly what it corresponds to, except over here, right? You know, so this means if I'm doing a full 360, you get a multiplicity of those particular ones. You can use it to do the speed up. All right, so you just take the 30 and divide by the sensitivities, that's what you get here. Or I could do a full 30 for everybody, and then this becomes higher quality as a measure. So that's all this is. Don't double count these. Over here, if I'm only doing 180 and they're 180 apart, right, you don't get to use the second one. Right? But here, when they're 90 apart, you absolutely do. Right? So I only have to go through 90 degrees if I want to be able to get it. And you'll notice here, they only count 1.5. You don't get to use the ones when they're on the back side. And they're on the back side half the time, so you only get half the effect. Makes total sense, doesn't it? Right? That's why it's not quite as quick over here. However, that's just another example the book had there, 91 specifically for a heart. But here's a 3 sensor system designed for a heart. It's a chair that you're sitting in, and they're all angled front. Instead of 120 degrees apart, they're usually 60 degrees So now all of the detectors, right? You can even have some that are less than that, but all the detectors are in the front, so I get all three measurements. Right? It's not always as easy to say just because it's a triple detector system that you don't get the full effect into the 180s. You do have to have specialized equipment for it, right? Anybody think what that might be for? Yeah, your arms. Because you got to be able to aim for the heart. Your arm in the way becomes a problem. So that gives you a spot to rest your arms while it's taking the image for them. These chairs actually rotate. So this machine will rotate the chair. So I kind of cut it off, but there's a robotic bottom point that just spins these. It is a nice feature because then I just have to move the detectors up and down and general height, right, relative, and that relative to you, I can just see that part of the mechanics here. So I can just elevate that up, and then there's a larger rotational basis circular, which will move it. But these type of things are a huge area where robotics and control stuff gets into medical imaging. All right, we feel good with these? So that's just a little contradiction, or I guess I shouldn't say contradiction, but a little extra information from what the book says. There are ones that are designed to handle that 180 problem. Okay, let's start talking PET. You can see this really lovely narrow bore again. You see the same type of a machine thing here that's set up. So if you're looking at this versus an X-ray machine, the only real difference is this has a little bit of a smaller bore and it's a little bit wider. Because this whole, see from that to here, this is where the detectors are going to go in that whole ring. And we need a fairly wide ring of those. But that means it's slightly more claustrophobic than a CT scanner when we're doing them. So there's that tube split into rings. We've already talked about this. This is where it happens. Positron comes out. Electron goes doot, doot, doot. They hit somewhere in here. And you get your 511 keV, Y511 keV, rest mass of an electron, which is also rest mass of a positron. All right, so I get exactly that going off in 180 degrees. Detectors on either side, that's what these little squares are all around. I can have multiple of these little rings. We do separate the rings to prevent light spread going too far. And away we go. Then we have to check, is it coincidence? All right. There's two types of these coincidence detectors. So I can set a time window. This is option one. This is the easiest one. I just say anything that happens in 250 nanoseconds, right? If it happens inside that window, I call it good. Right? I don't, since I'm calling anything and I'm not neglecting, right? Maybe it's 100 nanoseconds, right? Whatever the window with you pick for. If two events happen and it's possible for a straight line to be drawn between them without getting caught by the collimators, right? So it's possible for something to make that catch. So you'll have a list of which detector pairs go with which other detector pairs. But if I see those two and they both get a hit within that window, even if they're separated by some time, I don't care, it's good. Right? And I just have those windows. So the alternate thing of this is I actually measure the time between them. Right? That when I get each one, I get a time hit, I measure the time between them. So which do you think would give you a better image?
So one is just thresholding the time between them, and the other is just listing the time between them?
One, you have a window, and so any two events in that window
Oh,
connected.
I see. So the window's not based on the event. The event's just
Yeah,
arbitrarily.
there's a time, right, from this time to this time.
I see.
If anything comes in this area and they could have been part of the same event, they are part of the same event.
Well, then the second one.
Okay, so why wouldn't I always do that since it's better? I agree. It is better if you really know the actual time difference versus they just happened in the same period, right? You know, imagine if you were you're a detective now, right? Does it matter to you that you heard a gunshot and a scream within 5 minutes of each other, or does it matter that the gunshot happened and then the scream, as opposed to the other way around? It's pretty obvious, right? Yeah. So it helps us to know the actual time relations between them. So why not always do that? And sometimes think about the difficulty involved, right? What type of things could make it hard to get that type of a time difference measurement?
The physical distance between
Yeah.
your detectors and
Right.
the computer.
Like I said, you measure the time, and everybody just goes, yeah, right? How do you measure time?
The speed of light.
So, but here's the problem. Once I get relativistic, does the fact that your measurement speeds and everything, you're dealing with relativistic time intervals, does that have anything to do with measuring time? Did they do any relativity when you went through physics?
Not really.
So what's time dilation, simultaneity problem, right? Can I set and coordinate a group of clocks perfectly?
You know, relativity, yeah.
Can I get them perfectly at the same time? Now, as a matter of fact, you can't even say there is a consistent time zone between them. When you get down to relativity, you have a light cone. And anything outside your light cone might as well be in a different universe. Right? You have no way of directly accounting. You get it third hand, right? There's no way of saying exactly what's going on. If it's outside your light cone, you cannot measure it accurately. That's just a fundamental area. Well, we're dealing with those type of speeds, right? Everything we've got is moving at light speed. It's light, right? So we've got a kind of an issue here now on trying to measure them on those. And think about the distance, right? I can't send a light speed accurate time, right? So think about this. I want to be well below picoseconds to be accurate on that. Technically, for our measurement areas, I need to be somewhere in that picosecond range. How do I get something that accurate down to individual measurers around the ring? Well, I can't. If I have one source and I send it, the ones here will get it. If this is where my clock is, these will get it before the ones on the far side. And there'll be a skew. I can try to time the wires now between them to my circuits, but now it's only as good as those are. And what happens if there's, some particular electromagnetic field which causes interference down a wire, things of that sort. So there's a lot of problems that get into it. They're not insurmountable, right? We do have to deal with them, but these are fundamental issues that become, how do I actually do this super accurately? That's obviously an expense. There's another problem though. So that's one that's kind of what I would call the relativity or space-time issue problem. Remember what I mentioned earlier about those scintillators? What was the time period for our sodium iodine?
Couple hundred nanoseconds.
It's about 230, 240 nanoseconds from when a photon gets its peak light out of it to when it's down to 1/e. That's that still means there's light there, but that's a lot of time period. That's a big reason why those early windows were where they were at. Right? If I want to do time of flight stuff and I can't get below hundreds of nanoseconds, I'm sure as heck not getting less than a nanosecond, which is ideally what I need to do a good job of measuring my spatial difference in terms, think of that, a nanosecond for light, how big is that?
30.
Yeah, which is about what?
Thickness of your body.
So you figure you're dealing something, it's 11 point something or other inches, just say a foot for simplicity, right? So if I'm only at the nanosecond scale, I'm a foot. That's my imprecision zone. That's your whole stupid body, right? So if I want, this is why we say it's got to be in the picosecond range, right? If it's not at least 100 picoseconds, now I'm getting you down at technically it's around 80 picoseconds. You're at about an inch. So you really ideally want tens of picoseconds. That's like the sweet spot where things start working out. I therefore need a very fast. I don't need it to completely have discharged, but if it's not going to discharge for a good 1,000 or more of my 10,000 of my time intervals, it's going to be really hard to accurately pick your peak with all the buildup that goes on. So I got to get something in the small number of nanoseconds, then I'll still see another peak come off it and I can measure the peak. Does that make sense as an issue? And so it's going to be really important to us to screen out light. You'll see we'll cut our crystals and do all kinds of other crazy stuff to try to reduce crosstalk between successive hits. And it's all for this reducing the light so we get cleaner pulses. But yeah, ideally we'd like to. So if you can't meet all of those technical requirements, then you just do a window. And that's going to be good enough for binned data. If you want to be able, that'll just, now we're doing exactly what we did with X-rays where we smear it across the whole thing. If we get time of flight, we can actually say it happened in this little interval and we can get it down very precisely. I'll have a slide talking about this in a few things. So now you get to look at the crystals, right? This is something I want to add in because the book doesn't, they mention some of this stuff, I believe, but they don't really go into any serious detail. So that's a fairly typical crystal. See how they've got the cuts in the crystal, right? So that's photomultipliers on the back of the crystal. You cut into the crystal because then you can just put like foil or something or anything between them. You can even just frost it, right? And what you'll end up with is light scattered between those little regions will be cut down drastically. They become like little flashlights pointing up. Okay? Now, when you get a photon hitting inside one of those, one of the high energy ones, it's going to only hit one of those. Okay? When you get a second hit within a brief time period, the likelihood that's in one of those small subcrystals and not one of its neighbors, it's just not likely to just keep hitting the same exact crystal. Okay? So therefore, by doing that type of cuts, I can have multiple of those crystals at various points of dimming, and you won't get as much crosstalk on the light. So by a simple thing of cutting the crystal, I can drastically reduce crosstalk. Even when I go down to those photomultipliers, they'll still get something, but they won't be built on it. It'll be from a new, fresh area. So you'll get a distinct spike, and that spike will show up then on the photomultipliers. So that's kind of the trick to them. Yeah, like I said, long ago they dropped the thallium-doped sodium iodine, and they went to BGO, bismuth germanium oxide, or bismuth germanate, right? You can see, bismuth is one of your big areas here. Germanium's not that big, it's like 36 or something. But bismuth is 83, right? That's a really stupid high atomic number. So you're gonna really get, that's better than thallium, right, at 81. So bismuth is gonna have a really good cross section for you. You'll catch a lot of photons with it. In addition, it's 7.134, if you really want to be precise, grams per cubic centimeter. So it's about twice the density that you were getting with the sodium iodine. So it's, for both of our numbers, these are awesome, right? It's got a really good photo peak to Compton ratio. So on it's easier to distinguish between a direct on photo peak versus a Compton scattered one. That's really nice because it helps me to do it. This is not as big, but the Compton shield part is the important one to us, and we do want to distinguish the Compton scatters from the not. Problem, decay time, even worse. But this is the one almost everybody uses. And because of these features, particularly this one, it lets me find more of the particles, and since the positron emissions are really pretty low, you know, we just kind of got to live with that one. So we go, okay, it at least captures about twice as many of them coming through, and that's important to me. So all the more reason to cut the things and do what you can to save them. Now, more recently, there have been some other ones. So, you know, there's the two general families. There's these ones that are based off gadolinium, you know, and you can see most of these are silicates. You'll see the same silicate things in both family. It depends who did you bond the silicate with, right? So, you know, gadolinium is over here, and lutetium or lutetium yttrium combinations become the two big families of the crystals. These are the better generations. There is one where there's gadolinium and yttrium stuff too. So there's also some GYSOs, but those are not as common out there. And part of the reason is, you'll notice this one, Z, is effectively about 58. Very good, but it's not like, right? And effectively, none of these along here are that great either. It's got a good density though, but it's fast. 30 to 60 nanoseconds to get that drop off. This is in the range now that, you know, I can do time of flight measurements. The lutetium has even better stuff. It's got high Z. I've got a really good density. I got a really good decay time. 40 is a little bit optimistic. 40 to 50 is probably a, you know, but, you know, I mean, if you get a good crystal, you can probably get down to 40. You know, it's got 3 to 4 times the amount of light that BGO did. BGO doesn't give off huge amounts of light, but it catches a lot of photons. So even though it doesn't get great amplification. This one, even though this one gives off a lot of light, this one's somewhere around 71% of what the sodium iodine would do. It's got a really bad self-absorption though. So if this one gets thick, not a lot of the light gets out. So you make a lot of light and you lose a lot of light. So you got to be really careful with these. Effectively, light coming out of this is about the same as the light coming out of this, even though this one roughly generates about twice as much light as this one does. I think this one, if you call this a 1, this one's like 0.56 or somewhere around there. But on the actual light coming out, they're within a few percent of each other because of the really high self-absorption. Now, people have been working since this one has such nice timing properties. Like I said, this one, you know, they say 30 to 60. Nobody will give you a hard number for it because that one is a little variable, pretty heavy on how they make it. You know, by dumping in some yttrium, it lowers your Z because yttrium is much lower. The doping you can see here between it, that's not truly doping, it's actually a chemical, right? You've got the option that yttrium and lutetium can actually be used equivalent to each other, right? So what you do is when you make these, you adjust how much of these, and see the 1 minus X and the X. All you're saying, think of that as just alphas. How much do you have of the yttrium versus the lutetium, right? So you're just adjusting a ratio of those two. And then, you know, you're doping it with cerium. Now, you notice the Z drops because yttrium is nowhere near as good. The density drops a little, but it's still pretty darn awesome. You know, decay time gets even better. So the yttrium definitely helps you with that. And it's got even you know, it's about the same light zone on here. This one's actually a little bit better, because it doesn't have as much absorption. So you get to use more of it that's generated. The other kind of cool thing is, this is part of why I want to include the picture of the crystal. What do you notice with the color of each one of these? Notice in that one you've got the kind of purplish blue, got a little bit of a bluish tint, this one doesn't, right? So there's kind of a range of where the light is emitted on. You know, these ones here, usually 420 to 430 nanometers. This one's a little bit higher, 450, 480. This one has quite a range, but you can get it down in the low 400s if you need. That's the bluish tint, right? As you get down, you know, towards those fours, you're going into blues and purples. It turns out that that color range is nearly ideal for what's picked up with photomultiplier tubes. Photomultiplier tubes just, they amplify that color of light better. And if you think about it, that color of light is higher energy. As your wavelength gets shorter, you've got more energy. The photomultiplier responds better to it, right? So by getting one that's emitting light peak that's lower, you get a better photomultiplier response to it. So when these ones do give out light, you get a better amplification of where their peak goes. Whereas something like this or here, they're further away. So that's why I kind of wanted to include the coloration in here. So you just understand, right, you want those high energy photons. So when you see photon peaks of that, it actually affects things. There's a lot more going on than might otherwise be told. But this gives you an idea, right? They keep doping new materials in, improving some of the constants, away we go, and that makes it possible to handle other effects. We feel good? All right, let me go quick so we don't run out. We've talked about this geometry before. I just thought it was kind of nice in the picture. You can see the ring, and you get the idea of where the cross comes. Otherwise, you'll still get the same type of measurements around it. This was a good picture. I added the blue and the red lines to kind of get them. So if you look, look at A, for instance. See how one side of A hit, and the other one hit close enough to the edge it got absorbed by the collimator. But simultaneous with A, D was happening. And one side of it got absorbed, and the other one hit. But A and D were in the same window. So it effectively saw this hit from D and this hit from A and created AD, which just wasn't there, right? So that's a false one. That's what this random accidental coincidence is telling you. C, you can see something got content scattered, but just slightly, and it was on the longer leg of it. So it still ended up in an acceptable window, right? But effectively, it thinks it's going on this blue line, but it did have that little bit of a scatter to it that was going on, you know. So that's a scattered coincidence. That depends how well you cut out that peak, how wide you have to make it. Do you end up catching some of these that are scattered? What we want is B, right? Boom, goes across. That's a good coincidence. But to understand, just because you get a coincidence doesn't mean it's right. There'll be some of these fake coincidences in there, and it'll mess up your image. Okay. This is just for the time of flight stuff I was mentioning. If you think the little yellow blob there is the body, you can see it emits the source going on. By time of flight, we're saying the time it took to get here, you know, you've got a little window within it, whereas there you don't know the time window because it's a bigger area. So when you do it, this one you have to smear the whole way, whereas here, you know the region it is, and you know the ratio, how likely was it for them, because you can get a probability distribution to it. So I can narrow in, instead of just getting one big block area that I have to try to filter, I can actually get a probability distribution of where that came from. And the width of this distribution is all based off of the error of your time measurement, right? So I have a time error that's on here, speed of light. So speed of light times time divided by 2 gives me my delta window. So if you're within, 100 picoseconds, then, that means, the 100 picoseconds times the speed of light divided by 2 gives you that half an inch all around it. And I can narrow it down to that region. But it's not like it's a sharp edge, right? There's actually usually figure out a Gaussian type distribution. So we can, even if it's not perfect, I can still weight it more heavily towards the center and I get a much better area. So they mentioned you have to have at least 200 picoseconds. 200 picoseconds, it's a diameter of 1 inch. If your diameter is more than 1 inch, you're not really getting an awful lot out of it inside the body. So, this just gave the same thing, but I thought their equations were better, but I liked the other one did a better job of where the bodies were. But this one, I did like the fact that they showed you the ratio of the times to be able to get this in, as opposed to smearing it back. And they did an extra job times C times the other two. So, but there were certain, I thought the other one had a better graphics of the situation, and this one a better for the reconstruction. So, I stole both of them. But that's really what you're doing with the time of flight, is figuring out those time ratios. Good? Okay. Let me close this. We've got a couple secs here. I want to give you just a really fast statement. We'll finish this up next time. But I want to give you a fast idea of expectation minimization. I think it helps. Sometimes I've done this and sometimes I haven't. And the times I've done it, I think it was much more understandable to people. So we're going to do this for a very simple expectation model here on the first one, and then we're going to reconstruct the human body. We're going to do this for a Gaussian mixing model. But this is what expectation maximization is. Right? There's really 2 steps. Like everything else we've done, it's an iterative procedure. So I make a guess, and I'm going to refine it. It's a 2-step process. Expectation, the E step, and then the M step, right? The maximization. Right? In the E step, I took a guess, and I have data. So I took a guess at a model. Like, let's say I think it was Gaussian distributed, so I have Gaussian parameters. I took a guess at the Gaussian parameters. You have data. I can see how likely was that data to have come from, from the model that I guessed, right? And so if it's like a Gaussian mixing model where I have data that could have come from one of several different sources, I can say how likely it is to come from any of those guessed sources that I have Gaussian models for. So on the E step, I say, how likely was the data part of what I think the model is? Once I've done that, now I've kind of assigned data to models, then I can go back and, given that, can I figure out what was a better model parameter given how I split up the data? Right? So here I'm looking and seeing, given my models, how does the data fit? And then I say, since I've kind of reassigned the data with some knowledge now, I can figure better model parameters for them. And then I check and see, are my model parameters good enough? If not, I go back and I say, how well does the data fit this new adjusted model? It's not going to be perfect, right? And so I can kind of home in on it. This is the whole idea. Wild guess, home in on the parameters.
I have a question. Does the M step usually give you information on like what you can do to better your guess, or is it more like just an oracle situation? You have to have a search engine on the outside.
It's gonna, in this thing, I have to be able to get to the point where I can say this is a better model parameter.
Okay, so it does actually.
It has to give me an idea of how to get a model parameter.
Great.
Right? And that's, otherwise I'd be lost.
Right.
So the maximization step, I'm figuring out what would be the best, this is why it's a maximization, what would be the best parameters to pick. right, in some sense, based on my new assignment of data.
Okay.
Right? And there's a lot of ways you could split the data, so this is a very general procedure. I'm not gonna, we won't have time to go through how to write the whole code, but this is just for Gaussian mixture model. Imagine I had two different Gaussian distributions. So I just generated data from these, right? Now, since I have data, if I knew the yellows separate, yellow is an X, and X1 and blue is X2, I could take those and I could calculate their respective means and standard deviations easily. But what if I took the data from X1 and X2 and I put it into X and I sorted it? You now no longer know which one's which, right? But you do know it came from Gaussian, you just don't know the parameters. What could you do, right? Well, I could guess some Gaussian parameters, and I could go through each one of these, and I could take a look at, this is a basic probability distribution that you get, kind of your classic run, right? How likely is, the particular model parameters given your data? Well, that's how likely is the data given my model, and how likely is my model over, for each basically of my model possibilities. If I have equal data for each, roughly speaking, PB and PA will be the same, right? Because if you have 100 data points from each, the probability of a data piece was from A as opposed to probability of B is 50-50, right? So that essentially that becomes a semi-moot point here, right? They're equally likely. If one of them was longer than the other, we'd have to know that because that would adjust these probabilities. But otherwise, we just have those. Since they're Gaussian, this is your PDF. So this tells me like X based on your model parameters. So you can take a guess of the model parameters. We can find out how likely was that data part of that model versus your other guess. This will give me a probability, of that data being in a particular model. I can then use that to assign them. And then I can calculate new means and standard deviations for my models, and then see how likely was the data to fit with it again. I can just keep iterating that until it's done. And that's actually what we're going to do. We'll write MATLAB code for this starting on Tuesday.
So in this particular example, is the goal to get the actual mean and standard deviation of each distribution?
As close as we can.
Okay,
Figure out the mean and the standard deviation.
okay. And you also don't know which is from which sample?
You have no idea where the data came from. We generated two ones from different ones. You don't know what the distribute. You only know it was Gaussian, right? And now you have to, from that, be able to mix data. The only thing I'm going to tell you is of equal samples from each.
I see.
But they were mixed.
Okay.
And they're overlapping each other.
Okay.
So it's not going to be an easy separator, right? So how likely can we figure out what the original model parameters were? And you won't get it perfectly, but you'll actually be able to do fairly good, which is kind of nice. Whereas before, you wouldn't be anywhere near it. Right? And so this is just, we'll walk through this and just do an example. And it'll give you some idea of why this works on a small number of data. I mean, you give me a large number of data, I can home in on this really well. But with a small number of data, you'll still be able to do fairly easily. All right, we good? Basic idea? Think about it over the weekend, right? We'll walk through how to do code next time, and we'll break each of these down. But if you think about it in advance, it works. All right, have a lovely day, all. Oops, we don't want to show all of our code.